I think I'm going to get started. Thanks for coming this morning. We had a little mix-up last time this talk was announced, and I was in another building, and people were in this building, and so I'm glad to see we got every group in the same place here. My name is Rich Keller. This is another one in a series of talks interchanging information between NASA Ames and Google. And I'm going to talk to you today about a system that we've developed over the past 7 years, actually. This is quite a long R&D effort, SemanticOrganizer, which is an information sharing system for scientists and engineers who collaborate in distributed teams. Since it's been a long-term effort, and we started back in 1999. There's a lot of people I want to acknowledge. A whole bunch of my colleagues, actually Sean Wolf and Dan Barrios are with me here. A bunch of former teammates, and a key group of people are the engineering and science collaborators that we worked with, because what makes this system different is that it's tuned to the needs of scientists and engineers, and we're just computer scientists, so these folks are very important to us. Here's an outline of what I'm going to talk about today. I'll give you some introduction and motivation for why we developed the system. I'm going to not go through a demo itself, but I'm going to go through a bunch of screenshots to give you an idea of how the system functions. I'm going to talk about some applications that we've developed with SemanticOrganizer, and talk about some lessons learned that I hope will be relevant to you folks here. The group at NASA Ames that I manage is a group of computer scientists who are interested in intelligent information management. So that's an overlapping topic, certainly, with the work going on here at Google. So the motivation for developing the system was basically to assist large distributed teams of engineers and scientists in collaborating together on distributed projects. We have many different types of distributed teams within NASA. Some examples of teams that we've worked with include the NASA Astrobiology Institute, which is a large team of scientists in disciplines like biology and chemistry and geology who work at a number of different institutions around the country and internationally. And their charter is to understand the origins of life on Earth, really, and to inform NASA what we should be looking for in building space probes, in discovering life on other planets. We've worked extensively with NASA accident investigation teams as well as a class of team that we have applied our technology to. And we've also worked with mission design teams where there are teams of NASA folks who are developing new space probes and designing those. So across all these teams, there's a kind of common need, which is to share complex engineering and science data, right? So how are people at NASA sharing information? Now, I don't want to give you the wrong idea that NASA people are behind the times, but when we talk to people, we found email, sharing files via email is a major way that at least small collaborating teams are sharing information. Now, of course, that gets pretty tiring once your inbox gets full with files and files upon files. And when you scale up to tens or hundreds of people working together, obviously that doesn't work. So people use, what would you assume, file sharing systems, right? People dump their files that they want to share with their colleagues on a common file server, whether it's a FTP server or a web dev server or some kind of document management system, right? And so most people do that, and they say, oh, great, we're sharing knowledge and information with our colleagues because we put it on this shared file server. Well, wait a minute, not so fast. Our contention is that really conventional file sharing systems are completely insufficient for the purpose of actually conveying knowledge across a large distributed team. Number of reasons for that. I mean, there's very little discipline in organizing a file share system. I mean, someone sets up an initial directory structure and people start throwing their files onto the system. They may tweak it a little bit here and there, but there's really very little discipline, and there's kind of no librarian, right? There's nobody in charge of, what goes on that shared file system. There's an almost complete lack of metadata that's available when people use file sharing systems. I mean, the only metadata you really get is in the file name, right? You might get some kind of file naming convention that only the author of the file really would understand. So there's not much metadata. There's also a lack of kind of shared understanding, shared vocabulary and terminology for really understanding or describing the data that's being put on these file share systems. And I mean, I'm here at Google, and I have to say that you might be thinking, oh, well, let's just deploy a Google appliance and let's index the files. But most of these files are numbers, right? I mean, they're images and they're data files, scientific and engineering data files, and you really are not going to get very far by trying text-based approaches to doing the indexing. And finally, these systems, are basically hierarchical directory structures. They all rely on folders within folders within folders, and that provides you like a single indexing structure over the entire collection of information. And that's just really not adequate for the kind of information that scientists and engineers are generating. It's very highly multidimensional information, and we feel that there is no single indexing mechanism that can be used to appropriately index that. You might be fine if you look at your own directory structure on your hard drive, but when you start looking at other people's directory structures, hundreds of other directory structures, you get lost. You don't know where to find things. So what we say is that co-locating information is really not enough. What you get when you co-locate information from hundreds of people together on a shared file system is you get a bunch of non-integrated information, which is not interconnected and not contextualized so that you can see the big picture of what's there. I mean, after all, the idea of a collaborating team is to work together and to understand what information is available and what the team is learning as a whole, even if they're geographically distributed many time zones apart. And it's very difficult to use conventional file sharing systems for that purpose. Here's some things we are looking for in a file sharing system, in a knowledge sharing system. We'd like to be able to integrate across those islands of information, permit rapid and intuitive access and search over the information. We'd like to customize the vocabulary that the users use to their needs, because it's important to know that people have their own way of talking about data and information, and one size does not fit all. We'd like to be able to enhance the consistency and completeness of the information that is uploaded, and we'd like to be able to capture contextual information. So our approach is basically a model-based approach to storing and organizing information. So there's kind of three elements to this, and the first one is not very interesting. It's really the co-location thing. You need to make sure that all of the information is accessible from within one portal, if you will. It doesn't have to be physically located at the same place. The core of a model-based approach to information management is that you engineer a common model, a common information model that describes how all of the pieces of information that are going to be dropped onto this server interrelate and interconnect. So you develop and engineer a common vocabulary for describing all of the project information that's relevant to the project team. And then you contextualize the files and the information that you put on the server in terms of that common information model. You annotate the information in terms of the common information model that you develop. And I'll, of course, say more about this in the rest of the talk. So we call such a model-based information store a semantically structured information repository, or a semantic information portal, if you're familiar with that term. This is basically a conventional information management system like a database or a web server or a file server, plus an ontology. So you overlay or underpin the information that's being stored with this ontological model. And for those of you who may not be familiar with ontologies, they're more structured taxonomies, if you will, which allow cross-linking and cross-relationships between pieces of information. Now, in this model, repository users, what do? Well, first of all, repository users could be people, or they could be intelligent agents, other processes that need to access the repository and deposit information there. So what do the repository users do in this kind of model? Well, they upload heterogeneous content, just like they did with a file store. But there are two different types of content I want to distinguish here. First, there are the data files and images and documents and all the regular stuff that you think about for a file store. And then there is the stuff which is going to contextualize that information. These are records that provide context to the data and information that are uploaded in the files. So they describe people, places, things, activities, contextual items that are relevant to when the data was collected, how the data is used, and so forth. The repository users interlink and interconnect the information that's uploaded within a semantic information network structure, and I'll talk about that. And then they can search, access, and download the content. Okay, so I want to move on to describing making things more concrete now, describing our particular system. So SemanticOrganizer, the core representation is a semantic network structure. In a semantic network structure, there are nodes which represent key project resources, like people, places, and artifacts, and so forth, that are important to the project team, that the entire project team acknowledges, and they share a common understanding of these resources. There's a set of attributes which are associated with the project resources. It's metadata that describe those resources. There are a set of links which interconnect the resources one to the other and provide interrelationships between those resources. And there are also a set of attached files to these nodes, to these resources. So the files are what you would, again, conventionally think of as the information that's stored on a file server. So we've shifted the emphasis from the attached files over here, which is what's conventionally done, to this entire network structure which provides the context for accessing the information. We also have an ontology which specifies the types of nodes, the types of links that are defined for the project team that's using the repository, and a set of rules which allow you to modify the nodes in the network. And I want to go through each of these elements of our representation in more detail, and I'm going to use a concrete example from our work with the Astrobiology Institute. We have worked with folks who are, well, they're always out somewhere around the globe digging up these microbial mats. The microbial mats here, these algae mats, are sort of, well, they're kind of like slices of lasagna. They are in saline aqueous environments. And apparently the microbial mats are a very early form of life on Earth. And the astrobiologists are interested in understanding, how does this environment give rise to life, and how did it survive this long? It's evolved, but it's one of the earliest environments. How did it evolve? And how might we detect it on other planets? So they typically dig up these microbial mats. They transport them to NASA Ames. There's a greenhouse on the top of one of our buildings. They incubate them there. They poke them and prod them with various devices. They measure the oxygen concentration in these environments. They change the salinity of the water and the nutrients that are flowing over the water and so forth. And there's a large geographically dispersed team of collaborators who work on this project. So I want to describe now again what are the elements of our representation and how would you situate it within the context of this astrobiology work. So I first want to talk about the semantic network structure that I was illustrating. The microbial mat sample here is in the center. So what do we know about the microbial mat sample that might relate it to other things? We know, for example, that it was collected at Spring Beach, collected by a colleague, Brad Bebout, and stored in the greenhouse. So now we have 4 nodes in the semantic network now showing on the screen, and 3 relationships between the nodes. There's more, obviously. There's measurements that have been taken of the microbial mat sample. There might be oxygen concentration measurements, which were measured with particular instruments. There are cultures that were drawn from the sample material. They're cultivated by people. Mary Hogan cultivated this particular sample. There's a recipe, probably in a Word document, for doing that cultivation. There's an image associated with it that might have been imaged with an electron microscope. And so you see that there's a large, rich structure of information that provides context for this particular sample. And it's this kind of information that we hope to and do collect within SemanticOrganizer. I want to illustrate the notion of the ontology in the context of this example. The ontology defines the types of nodes and the types of relations again. So you see a number of different types of nodes here. Nodes or classes, however you want to call them. We have sites and people and projects and various types of measurement and equipment and so forth. It looks like a class hierarchy, if you will. And of course, it's much more complicated. I'm just showing you a little bit of it. And there are also specified, defined links between these different types of nodes. So for example, a culture can be cultivated from a sample, can be cultivated by a person, can be pictured in an image, and so forth. So the idea behind the ontology is that it provides constraints on what can be connected in the network. So you can't, for example, connect a culture to a document with the cultivated from. A culture is not cultivated from a document. So the important thing about the ontology, again, is that it defines these constraints, and it provides a model for what's correct to connect to what other things. It provides structure. The ontology is actually part of a much larger ontology. We have a unified kind of master ontology that we've developed that holds the nodes for all of the different teams that we work with. And what we do is we subset the ontology for particular subsets of people who are working in different groups. So they don't all see all of the 300 classes in the master ontology. They see subsets of them that are appropriate to their language, their concepts, what they're trying to do with their data and information. And we use an RDFS-like ontology for those of you who are familiar with XML RDF. Next, I want to show you an example of a rule. Here's a fragment of a semantic network. This says that there's a sample map 654, which is collected by Brad Bebout, a person who works in a biogeochemistry laboratory. Suppose we have a rule that says if a sample S is collected by a person P and the sample S has no custodian, then the person P is the custodian for the sample. So what this allows us to do is to infer this missing link here and allows us to extend the knowledge that we actually have in the network structure. These can chain together. If a person P is a custodian for a sample and the person works in a laboratory, then the sample is stored in the laboratory. So this, again, allows you to infer that mat is actually stored in the biogeochemistry laboratory. Okay, I want to now make things again more concrete by showing you what the users see when they do their work with Semantic Organizer. This is our browser-based interface. And the browser-based interface is essentially a browsing mechanism on top of the semantic network structure. So on the right-hand side, you see the mat sample that I've been talking about. It's called here Spring M4B. Okay, it's the mat sample at the center of that semantic network structure that I showed you. On the left-hand side are links to the related nodes, which are one step away in the semantic network structure. So on the right-hand side, again, is a description of the current node, the focal node that you're pointing the browser at. And there's metadata down the right-hand side here. You can see the metadata, description, collection date, collection time, what microorganisms might have been found in there, and so forth. And again, on the left-hand side, you see links which emanate from that node. So you see that this mat sample was collected at Spring Beach, collected by Brad Bebout, collected during, et cetera. And when you want to navigate through the semantic network structure, you click on one of the associated links or the associated nodes in this case. Here I want to traverse the network, traversing the pictured in relation or link to get to the SPR M4B excised photo. And when I click there, what I'll do is I will navigate across the semantic network link to this particular node, which is the photo, one step away from the previous link, previous node, sorry, which is this sample. So there's a reverse link. These are bidirectional links. And you'll notice, of course, that there are different relations on the left-hand side, different types of nodes which are described on the left. There's the camera that was used in developing the picture and the person who imaged the picture. So these are all typed, right? And the displays depend on the type of node that you're currently visiting. So, same for the metadata. The metadata is different here as well. I want to show you how users would interact with the network and change the network, edit it, and so forth. And I understand there's work here on Google Base where there might be some relationships between what we've done here and what Google Base is doing. So the user would click on the edit links, and what happens is the left-hand side expands, and you see here additional hyperlinks that allow you to modify the links that already are there. You can cut the links. You can link to different items. And actually, on the bottom here, I want to focus on creating a new type of link to a new object. In this case, let's imagine we want to publish this paper in a journal article. And so there's a new journal article that we're developing, and we want to make this link. Now, you can do it in two different ways. If the publication is already inside Semantic Organizer in the network structure, you can click on Link to an existing publication. What happens in that case is the system goes out, it searches for all items of type publication, and it presents them to you in a search result type page on the right side here. And then you can just select whichever publication it is you meant to link it to, and then it will create that link. The other option that you have is to create a new publication. Suppose the publication isn't in the system yet. You click on the new link, and then what you get up is a browser-based form, which you fill in. You browse to your local drive. You know the whole story. You upload it. It might be a PDF file. And down here, you fill in metadata for that particular item. One thing to note here is that some of the metadata is presented in the form of list boxes where you select an item from the box. Unbeknownst to the user, of course, we're presenting to them other nodes in the network that they are going to actually link as author or project. So this is kind of a sneaky way of getting them to expand the network structure beyond the initial link that they intended to make. So when you say OK, what it does is to create the publication, which you see here on the right-hand side with the metadata. And on the left-hand side, aside from the link that you wanted to create, which was has figure, okay, you wanted to create this link, it also created a link for the author and the projects that were related because of the selections that were made. Okay, since it's Google, you're probably wondering, what sort of search mechanisms, how do you search the information in the repository? And we have a variety of different mechanisms. We actually have, I think, mechanisms that are more powerful because we are more structured than the web is, right? So what we have here is a search box. I guess you can see better over here. The search box provides a number of options. You type in the search string, and then you can search within files, within fields, or within names. So searching the names, the name option searches the names of the nodes. Searching the files searches within the attached files, within the text of the attached files, if there is any text. And searching the fields searches the metadata fields associated with the nodes. And then on the bottom, you specify the type of node to be searched, or the class of node. You can search all node types, or an individual node type. You can go further than that. We have some more power here, which allows users to get more precise results by searching the metadata fields and making constraints on the metadata fields. So you can search for a particular publication type or a particular author, and it will add additional constraints onto your original search. So that kind of concludes like the basic overview of the functionality that we have and how people interact with the system. I want to talk about a variety of different features that are, well, maybe a little bit more advanced features or additional features that I thought you might be interested in. So beyond the two search mechanisms that I talked to you about already, we also have kind of an advanced search, which is a semantic search. And this is actually work that my colleague Dan Barrios did to develop this approach to searching for extended patterns of, or extended chains of links and nodes. So you can actually execute queries like find all DNA sequences associated with stromatolite samples collected at the field site named Stromatolite Beach. Okay, so this is a simple interface that Dan put together that allows you to specify these types of extended chains, which are then executed by matching them against the semantic network structure and finding results in that way. We have in the system also email discussion lists. These are conventional discussion lists in many ways. You just send, any collaborating group can create one or more discussion lists. You can send email to the discussion list. It gets distributed. Okay, that's fine. What's different about our system is that it makes a node out of each email message that's sent to the list. And what we have then is this kind of a display that's possible. You see the email body here on the right-hand side and the metadata associated with it. And there are links from the email messages to other items in the system. There's a followed by and preceded by link. What email followed this and preceded it? Who sent it? Where was it sent to? And so forth. So what's interesting about this actually is that for a distributed team, it's actually quite valuable to be able to link the email messages to the data that's related to concepts that are mentioned in the email. And so we have this thing called discusses. So you can, if you want, if the mail talks about some kind of field trip that a scientific team took, you can connect that email message to the representation, the node for the field trip. And then all the data is arrayed around that node. Now, of course, that's pretty tedious. And one of the things that Dan also looked at was actually extracting from the text concepts that are, or instances of concepts that are represented in the semantic network structure automatically and presenting them to the user as candidates for linking to the email message. So how this is done is basically the text is parsed and marked up to identify nouns that match the names of nodes and verbs that match the names of links. And it's also looking for references to attribute values, for metadata values. And it's also using WordNet to allow inexact matches between the node name, for example, and the noun that's found in the email message. So it's forgiving in its matching process. And then he combines them with in a relevancy ranking score and combines a set of factors numerical factors based on frequency of occurrence of various nodes and links in the email message. And then it presents, the idea here is to present to the user, well, John Spear was definitely, we believe that John Spear is definitely mentioned in this email message. And we rank all of the nodes in the network against the email text to determine the relevancy rank. We have also, we've also realized that people don't want to leave their existing tools, of course, and go to a web page to do all their work. So we've tried to integrate where we can within their existing tools. We've developed Microsoft Office macros, which allow you to, when you're saving a document, to save it into Organizer directly. When you're resaving it, it will update it. It asks you for a little bit of information in the macro. We've developed a shared image annotator, which is a synchronous collaboration, whiteboarding kind of tool that you can launch from within the browser, within SemanticOrganizer, and all people who are using the tool at the same time can see the image, can annotate it. It can be saved back into the system with the annotations. And we've developed an API which allows us to connect to other external processes and agents. We've used the API to connect real-time images and measurements which are coming from experimental equipment. And it's been very, very useful for all the work that we've done. The architecture of the system looks something like this, an interface layer, which I've talked about most of the elements of this. We do have a set of alternative viewers for the semantic network structure. We don't just have the browser-based interface. We have some other techniques for viewing the structures in the semantic network as trees or lists and visualizing things in different ways that are appropriate to different teams. The ontology is, at this layer, this is the representation and reasoning layer. The ontology is represented there. The semantic repository contains the instances of the nodes in the ontology and the links. There's an inference engine, which is there to run the rules over the repository. And then there's all the mechanisms for the semantic annotation work that I just mentioned to you and the email work. And much of the architecture actually was developed by Sean Wolf. And the lowest layer is, well, we've built on top of the Java Expert System shell, JES, for the rule engine. We bottom out in a MySQL database. The web server runs Apache and Tomcat, and we're doing things with Java servlets. Okay, let me go on to some of the applications, aside from the astrobiology application. So I wanted to just mention the status of the system. We initially deployed in 2001. At its peak, we had over 400 registered users from within NASA, and some at some universities as well. We've hosted over 30 different projects. The network structure is rather large. I mean, I guess it's all relative, but there are 45,000 nodes and 160,000 links in the repository. It's not like all of the web. So, but anyway, it gives you a feeling for what we've done and what kind of usage the system has gotten. So we have a number of different application areas, and what we've done is to market the system in different ways to different communities, because SemanticOrganizer just doesn't cut it for a scientist. They don't really know what that's all about. So we just call it ScienceOrganizer for them. For the team of accident investigators, we called it Investigation Organizer. The Software Organizer is a system we're working on now, a deployment. But all of these different versions are really the same system using different cuts through the ontology is what it is. So you can build additional applications on top of things if you want for a different community. But basically, the basic mechanism is all in place, and it's just a naming thing. We've also worked with people who do mission design, design of spacecraft, and we have worked with the NASA New Business Office. This is kind of a customer relation management application that we built for them because NASA's looking for partners like Google. So just let me say a little bit more about the various teams that we've worked with in ScienceOrganizer. We have, I mentioned the astrobiology work. We've worked with also folks from the funded by the NIH at Tulane University on an African malaria study. We have a large collection of Martian meteorite imagery from Johnson Space Center and also from Ames. We've worked with the Mars Exploration Rover team, the team that's still functioning down at JPL, operating the rovers on Mars. And we worked with them on developing a system to manage scientific hypotheses that were made by the team and the relationship between those hypotheses and the commands that they send up and the actions of the rover. We've worked just recently, I guess Dan was involved most heavily with this effort with the Monterey Bay Research Institute, MBARI, down in Monterey Bay. And we worked with them also on connecting their scientific hypotheses to the actions that they were going to have the submersible rovers engaged in the campaigns that they were conducting out in Monterey Bay. We've also worked with the Mobile Agents project at NASA Ames, where they're doing simulated surface exploration of Mars. And what we've done is to serve as the repository for measurements that are taken out in the field by the simulated astronauts, images, GPS measurements, voice notes from the simulated geologists that are doing their work. And ScienceOrganizer, again, was the repository for that work. This just gives you the idea of the kinds of use cases that people have brought to us, different ways in which they've wanted to use the system and have used the system, everything from education to writing papers and proposals and acquiring data from remote instruments. It's quite varied. And again, we can engineer the ontology to meet their needs in all these cases. So let me talk to you now about Investigation Organizer. That is an interesting application and perhaps the one that we're most well known for because we actually deployed this for the Columbia Accident Investigation and helped the Columbia Accident Investigation Board organize all of their evidence and information that was used in that particular investigation. So in these large accident investigation teams, there's a huge amount of information that gets kind of funneled to the investigators all at once. One day everything's fine, and the next day there's been an accident, and they're getting operations logs and inspection logs and training logs from people, and they're interviewing witnesses, and they have transcripts, and they have all this information that needs to be coordinated and organized and interconnected. So I want to give you an example of how we apply the Semantic Organizer methodology to the accident investigation work by starting with this little example here of an incident that happened at NASA Ames maybe 10 years ago, where they were testing a rotor wing for a helicopter in one of the big wind tunnels over at Ames. I think I'm supposed to say it's an Army wind tunnel, not a NASA wind tunnel, but that's, so we didn't do it. But somebody forgot to tighten the bolt, is the bottom line, properly. And so this, when they started up the wind tunnel, this whole thing, the assembly just flew off the test stand and did a lot of damage to the side of the wind tunnel. And fortunately, nobody was hurt, but there was an investigation. So what does the semantic network structure look like in this case? Well, it's a little bit different structure, but it's the same idea. We have a node representing the investigation itself. There are linkages associated with it. So the rotor wing mishap investigation has a system that's under investigation associated with it, which is the rotor assembly. The rotor assembly has associated with it a subpart, which is the rotor pitch link. The rotor pitch link was found at a wind tunnel, a particular location in the wind tunnel. There is a design record associated with this rotor assembly, which represents the design schematic. The schematic supports a hypothesis that there was improper bolt tightening because the schematic actually has the torque specifications for how tightly the bolt should have been torqued. So it's really the same concept. I'm just showing you it in a different context. The ontology is a little bit different, but you see there is sharing across this ontology and the other. There are some specific types of things, like there are specific subclasses of evidence, and there are specific types of groups that we didn't have in the scientific domain. But we have still people, and we still have images of various types. So there's sharing across the ontologies, across the models. Different types of linkages here. And we started doing this work with the helicopter rotor wing example just to get our feet wet. And then the contour, there was a contour mission, which was a comet following mission. And unfortunately, that particular craft blew up on exit from Earth orbit as it was just about to start on its path following comets. And we were brought in at that point to kind of shadow the investigation, to be in the background, not to be, up front and be used by the team, but just to be there and to see whether we could get the system to work properly ourselves. And actually, we were so successful with that process that they saw what we were doing and brought us into the investigation proper. And we actually supported that whole investigation, which was probably 6 months long. Now, at that time, we got a kind of a reputation at NASA headquarters for having some kind of a tool that would help with accident investigations. And when the Columbia accident happened, we were on a short list of teams to come and help. We spent many days and many weeks in Houston assisting the Columbia Accident Investigation Board. We stored virtually all of their evidence and helped them connect that evidence together. Some of the interesting things that we did with Investigation Organizer was to help them model the accident in itself. So that's part of what the accident investigation team does, right? They try to figure out what's the cause of the accident. So we developed a fault tree structure. So we represented faults and subfaults in the semantic network structure, and then depicted it as a semantic network, as a fault tree representation hierarchically like this. They also developed timelines and time sequences for the accident, and we developed those and illustrated them in an editor-like mechanism. And so we helped with a number of different activities of the board. Software Organizer, I don't think I'm going to have a chance to say a whole lot about Software Organizer because I know I'm running out of time. But this is a new application that we have begun over at NASA Ames. And this is to help the software assurance people who accept delivery of software from NASA vendors for missions. So what we do is we get all this software in, and it's our responsibility to integrate and to determine whether we got what we had specified. And it's kind of a daunting problem because typically software vendors will just deliver the product and they don't deliver much information or metadata about the product, and it's hard to interrelate the pieces of information. So Software Organizer is all about trying to organize the various artifacts that are delivered by the customer, by the vendors for NASA, and help NASA do a better job of software assurance. This just gives you a sense for the upper ontology for Software Organizer. I'm not going to really say much about the various types of artifacts that are represented here. This is just a depiction anyway. But I want to go on to the last part of the talk, and that's lessons learned, some of which I think are probably applicable here to work going on at Google. Lesson number one is that even though people use the web, people don't think about the web as a network structure. People are not generally comfortable with network structures for storing their information. They're very comfortable with hierarchical folder structures. So that's a huge obstacle to a system like this. We tried to, people were always asking us, well, I've got this folder structure in here, and how do I put that into the system? And so we actually did develop a mechanism for folders within the semantic network structure, but it really wasn't very successful. It was a bad match of this hierarchical and network structure together. We had to type the folders, and typed folders where you could only put in one type of thing were not very familiar or useful to most people. So this is kind of a caveat that says, hey, you need to do a lot of work to provide mechanisms to make people comfortable with the kinds of representations they're currently using, as well as new representations that you're introducing. Lesson number two is, well, it has to do with organizational style and how people like to organize their information. So as I guess you gathered right now, by listening to the talk, you understand that this is a very structured representation for information. You go into people's offices and you look at their desks, and some of them are very meticulous, but most of them are messy. It's messy in there. And the people who were less tidy in the way they like to have their information organizer, where they really rankled with some of the restrictions that we put on them. They could only connect certain things together in certain ways. Now, we worked around them. We provided anonymous types of links. They could link things. You can link any two things in the system. And then we later on go in and engineer a proper relationship. But I'm just saying that the organizational style is an important thing. Some users didn't feel it was important enough to them to put in the kinds of metadata and the interlinkages that we were asking for. So again, that's an important thing to keep in mind. And we've focused some of our research on how to get beyond some of those problems. Lesson number three, navigating the information space is very difficult. We have hundreds of thousands of nodes and links. How do people get a sense for where they are in this structure? Our node browser interface just focuses them in very locally on a single node, a single focal node, and the things that are right around it. We need to have better mechanisms for visualizing the semantic network structure overall. And I think there are actually some very interesting work that can be done here in semantic web visualization research. There's a lot of knowledge and information in the network structure, in the representation, that might allow you to abstract over the representation itself and present it in useful ways to users. And lesson number four is that automated knowledge extraction is a key part of what you need to do to make this kind of a system work. You can't just be relying on users uploading information, because users need access to large information stores. They need access to databases. and to information on websites. And if we're going to import some of those things into our system, obviously that can't be done totally manually. So we've developed a number of different techniques. We have inference rules. We have this annotation work, which extracts annotations from text. We try to connect with other systems in many different ways. So I'm going to close here. Let me just revisit the key idea, which is to use a common information model to glue together the disparate data that's presented by users in a file sharing system. So we want to glue the information together into a coherent whole and use model semantics to check the validity of the information and improve the consistency and completeness of the information that's entered into the repository, and then use the contextual information as a mechanism for enabling users to access, retrieve, and search the information that they've entered into the system. So that's it. Thank you very much for your attention, and I'll take questions if there are any questions. Thank you. Questions? You're told to use the microphone. At least that's what they tell me.
Based on your experience, do you have a feel for what's the minimum size project or team that justifies the overhead of a system like this?
Okay, so the question, thanks. The question was about the minimum size team that you might imagine using such an infrastructure. Well, I mean, we've had teams as small as 2 use the system because they were collaborating across firewalls. They didn't have mechanisms in place to share information. And I guess the problem is on our side where we have to engineer a new domain for them, a new maybe additions to the ontology or set up the ontology. But typically it takes us maybe a week or 2 weeks to augment what we have and generate a new system for people. So it's actually, I think that there's a lot of work in understanding people's work and what they're trying to accomplish in their work and to represent the concepts that are important to them. So I think where the work comes in is the engineering aspects of knowledge engineering, understanding what would make access to the information most valuable for the team. Yeah.
At one point, you were mentioning, it sounded like there were, in some cases, not just one group that was using this tool, but like you mentioned investigation teams, for instance. Is this something where sometimes like some people who weren't originally part of the team will just kind of get lumped together and said, okay, we need you people to investigate this thing, and here's the system that you're going to use? I guess I'm wondering, do people need to come up to speed on using this system in a hurry, and how do you get them trained?
Great question. Yes, they do, because it's, as I mentioned, some of it is really not intuitive for people. Some people take to it quite easily, but for example, in the case of the Columbia accident investigation, you had people running here and there, flying to the different accident and debris sites. And so the way we handled that situation, where we didn't have time for training, was that we actually supplemented the team there, and we were a presence there. And we taught the people who were, I guess, just one level under the investigators how to insert information and how to work with the system. But in general, we have the typical thing. We have training materials. We have tutorials, and that's how we would handle it for a more typical team. Any other questions? Okay, I guess that's it then. Thank you very much.